Hey guys, welcome back to another Flowco e-learning series. My name is Matt Young, and today I have the pleasure of Will Nelles coming out from West Texas to join us today.
Yeah, well, thanks, Matt, for having me. I'm really excited to be here.
Yep, me too. Thank you, Will. And guys, today, like I mentioned, we have Will. He's part of the Estes group here to talk to us today about high pressure gas lift. And so we'll get to spend a lot of time going into that. But just to give everybody an update, Will is the Director of Technology and Innovations with Estes.
That's correct.
And you hail out of San Angelo, Texas, right?
Right. Yeah, roughly the Permian.
Yep. The pretty part of the Permian.
That's
right?
correct. Yeah. It's a little more water, a few more trees. Great place to live, but close enough to be part of the action.
That's right. Yep. Just to be dangerous, right?
Right.
So, yeah, guys, today we have Will on. And one thing we wanted to do was kind of capitalize on the news that has come up the last couple of weeks with the merger of Estes, Flogistics, and Flowco into one integrated company to provide surface compression and downhole gas lift components as well.
Yeah, and I think that's going to be a real exciting partnership. I mean, I've thought for many years in my career, well, let's see, compression is required for gas lift, and downhole gas lift valves are required. So why don't we push them together? And we've managed to pull that off. So I'm so excited about what I think we're going to be able to deliver to our customers into the marketplace.
Yeah, I agree with you. And it's been a piece that the gas lift industry has lacked, not having access to that compression. And so excited for it. And frankly, we do these e-learning series every month. And with the announcement a couple of weeks ago, I thought, what better way to kick off the e-learning series than to have you come on board and hopefully educate everybody about high pressure gas lift and kind of talk about both the use of high pressure gas lift and then more so that kind of planning piece as to, eventually we have to switch, right?
Sure.
How do we switch? What do we switch to? And probably more importantly, when do we switch, right?
Sure. Well, and Estes has been involved in high pressure gas lift since the earliest days. I mean, we're going back to 2016. Mm-hmm. So,
long time in the unconventional oil field, right?
Well, it really is, and it's been fun to watch. I've had the privilege of being involved in high pressure gas lift since the earliest moments, and so while maybe we don't consider ourselves God's gift to high pressure gas lift, we've certainly been there and we've learned some things, and I think we have some ideas, and we just want to share that and partner with operators and expand this really great artificial lift method. And what better way to do it with Flowco production solutions. And as we talk about converting from high pressure gas lift to conventional gas lift, I mean, really what we're trying to develop, I feel, is a gas lift solution from cradle to grave, and now we're just perfectly positioned to do that.
Yep, I agree. And really from like our training series today, those were some of the things that we would like to talk about, and of course get the input of the audience as well. And really, I think from our end, one of the big things is just simply define, and get your expertise on it, is what is high pressure gas lift? How do we classify it, or more so, how do you guys classify it? And really see like, okay, when we're talking about high pressure gas lift, what is it?
Sure.
And then from there, I think about all the different kind of subsections below, just simply what is high pressure gas lift in terms of like, what's the best applications for it? Is it new wells? Is it older wells? Is it deep wells? Is it shallow wells? All your different unconventional classifications of these horizontal wells. And I hope we can, in this discussion today, we can really dive into that and get some good input out, get some good technical references out to the group and go through that.
I think we can do that.
Perfect. I think so too. The big question is, can we squeeze that all into an hour, right?
We better get with it.
Yeah. So guys, today, really, while we had Will trapped in a room, we wanted to pick his brain about, things that I talked about. What is high pressure gas lift? What are the best applications for high pressure gas lift? kind of back to what is high pressure gas lift. How does it simply work? Some operators are very experienced in it. Some are not. And then so hopefully we can kind of standardize that understanding. One of the big things that we get asked quite a bit, both from your standard or your traditional compression as well as your high pressure compression, is how do you set it up at surface in terms of the plumbing? Are we setting it up for a short-term usage? Do we want to plan for more long-term and have that flexibility to change from one to the other? So those are some of the things that I hope to talk about. And then probably one of the big questions is, when do you switch?
Right.
When do you go from high pressure gas lift to whatever we want to call low pressure gas lift or traditional gas lift? Because eventually we know we'll have to switch in most cases, right?
For sure.
And so how do we determine that? And then more so, once we determine that, how do we make that switch?
Sure.
And so lots of good topics to talk about, and really dive into that.
Yeah, let's get going.
Okay, perfect. So, one of the first things, like I mentioned, is, Will, can you help us define what your expectations are, what your thoughts around high pressure are? Like, what is high pressure in view of you and then also the Estes group?
Yeah, well, that's a question that a lot of people are asking, Matt. I mean, what is it? I mean, when you look in the textbooks for gas lift, high pressure gas lift doesn't appear much there because it's a relatively new artificial lift method or a variation on gas lift, right? It's not radically new, but it is a variation on it. So it is not really in the textbooks yet. I was in Norway recently at the gas lift workshop, and one of the points that I was trying to make is just to put some definition on it. So I would say probably several things, and maybe there's a slide here that you can pull up.
Yeah, we can share that with the group and take a look here. There we go.
That would be helpful is to look at some forms of gas lift that people are familiar with. So I would start with annular gas lift. Most people are familiar with the concept that it is conventional gas lift except reverse flow.
Correct. Yeah, we're injecting down the production tubing, flowing up that tubing case and annulus.
That's right.
And utilizing that increase in surface area to help reduce any frictional pressure loss, lower our flow and bottom hole pressure.
Yep. And in annular gas lift, there are still conventional or gas lift manholes. There are multiple unloading stations. So a second form of gas lift that people are familiar with is what we call poor boy gas lift, right?
You see that in a lot of the older brownfield basins, Arkoma Basin, Barnett Shale, Fayetteville over in Arkansas. There's a lot of what you deem poor boy gas lift because reservoir pressures are low enough, wells are relatively shallow that a standard 3-stage compressor has enough discharge pressure to inject around into tubing without the use of multiple station gas lift valves.
Right, and so some of the defining characteristics of poor boy gas lift is they tend to be shallow, but most importantly, it's single point, and you go around the end of the tubing.
Yeah.
So then how do we make high pressure gas lift out of it? Well, I see really it as a marriage of annular gas lift to poor boy gas lift. You add the two together, and I'll let you jump to the next slide. I think we have depicts that a little better, that high pressure gas lift was simply three things. We call it HPGL is kind of an acronym, but number one, it is single point injection. There are no multiple mandrels or unloading stations, as some people would call them. Number two, we lift around the end of the tubing. So it is the end of the tubing that is that single point of injection. And then three, we produce up the annulus. And so if someone were to ask me, how would I define high pressure gas lift? It would be those three characteristics.
Okay, and that makes sense. And like when I dive into these from a hydraulic standpoint or a flow and bottom hole pressure standpoint, the things that you just mentioned there, how I see, the benefit of it or kind of the appeal of it, right, is the single point injection. So that's more of a mechanical thing. Is, if we can lift at one single point, we're effectively using our injection gas to reduce our densities of our fluids. Hopefully we're not inducing any kind of, potential fail points to change that point of injection. When I think about lifting around into tubing, with these unconventionals, they're highly deviated before you even get to your kickoff point. And then, of course, you go through your curve and into the horizontal section. So when I think about that, it's like, well, if we're trying to simply reduce the density of a hydrostatic gradient, which is what gas lift is,
right,
then we can take that into tubing. And again, depending on operators' comfort level and, fishability and all those things, we could potentially set our into tubing at, say, past our kickoff point. If that's 45 degrees,
right,
if it's 60 degrees, if it's 65, whatever we define as our into tubing placement. But what that tells me is now we're reducing the density of a greater column of fluid and help lowering that flow and bottom hole pressure.
That's right. And that's a very important characteristic or aspect of high pressure gas lift that I think I would want to highlight to anyone considering high pressure gas lift is we're not lifting from, the top point or the second point or the third point, but we are lifting from the lowest point possible from day one.
Mm-hmm.
Typical kickoff on a high pressure gas lift well is, several hours. I don't spend as much time in the field and doing the commissioning and the kickoffs.
Right.
But what I recall from the early days is we're talking, 2 to, maybe 6 hours on a long one, but
Mm-hmm.
Kind of in the middle it was about 4. But really to lift from the end of the tubing, and you brought up the idea of where is that? I recall we were commonly in the 60 to 70 degrees. You're very deep into the well, much deeper than an ESP, and I think maybe even commonly you see gas lift valves. So we're lifting from a very deep point early on, and so all of that column of fluid now is being lightened.
Mm-hmm. Yeah, you hit that density reduction, and you talk about like time to kick it off. In my head, really the time function is just the displacement value, right?
Sure.
If you're injecting down your tubing and lifting up your tubing casing annulus, then really your time to get that gas from surface down to your end of tubing is just whatever that displacement value is to displace the fluid out of the tubing, which of course is a lot lower volume than it would be injecting down the
annulus.
Exactly.
Yep.
Yeah, down the casing. Yep. So that's interesting. And then bring up the produce up the tubing casing annular section is that in general is a very valid application for most unconventionals. And the reason why a lot of operators have been driven to some form of annular flow gas lift, or really annular flow production, is just simply the restriction of our casing well bores.
Right.
Like it would be great if every single well had 7 5/8 casing.
Sure.
Because then we can put essentially whatever tubing size we want. But for the most part, wells are going to be confined to 5.5 or maybe 5 inch, or if we're lucky, maybe 6 inch casing, but typically it's going to be 5.5, which essentially means the biggest tubing we can realistically fit is 2 7/8 tubing.
Correct.
And you look at wells like a Delaware Basin well, or maybe a Bakken well or Powder River, where initial or IP production rates are relatively high. 2 7/8 tubing just isn't going to cut it in terms of production handling. And so being able to switch to that annular piece increases that surface area, reduces that friction, and allows operators to handle those higher production rates.
Yeah, and just to be real clear with our audience, we recognize that some joining us here today, may not think through all the little details. But when you say the tubing, the 2 7/8 may not be adequate, really what we're talking about here is the cross-sectional area,
Mm-hmm.
the flow path of fluids and gas, anything coming out of the well. We're trying to get those fluids potentially up a tubing, a piece of pipe 2 7/8 inch in diameter.
Right.
And when we're talking about wells that are producing multiple thousands of barrels of fluid per day, we've seen some as high as 10,000. You just think, well, gosh, that would really have to be coming up at some awesome velocities, and then fluid friction becomes an issue, and then you have pressure drop, and none of which are conducive to high performing gas lift wells. It's
Yeah.
just not in the physics of how gas lift works. So we need to get a bigger hose.
Yeah, and that's a really good point. And, that's one of the things that I like to clarify here is that if we use just standard 2 7/8 tubing, you get roughly about a 4.5 inch, cross sectional area in square inches. Well, if you just simply switch to the annular space between the casing, 5.5 casing, 2 7/8 tubing, you almost 3 times that surface area just simply by changing your flow path. We're not changing the geometry of the wellbore. We still have our standard tubing that most operators can source from anywhere.
Right.
It matches most casing sizes that we see, but just simply changing that flow path really increases, like you mentioned, that hose size to handle those higher production rates.
And it's kind of a freebie increase in our flow path, right? I mean, we're not having to buy larger production tubing that costs more. We're not having to buy different casing. We're just working with what we have here. So operators aren't spending any more money doing anything. We're just doing it smarter. It's kind of a work smarter, not harder type of situation, right?
And that brings up a really good point is, with the unconventional wells, and actually that kind of leans to Tony's question or comment, is that, one of the last things we want to do with unconventionals, because their production fluctuates relatively fast over the course of the well's life, is less workovers, less interventions, because it increases costs, it risks, fishing jobs and all the things associated with bringing a workover rig on location. And so when I look at things like annular flow, one of the things I think about, and we'll talk about on surface setup, is planning for a change and then making that change. If it's flow area change, annular to tubing, if it's high pressure to low pressure, but having those plans in place so that when you get 6 months or a year down the road, you're not saying, oh crap, what do we do now?
Yeah.
You already have that plan in place. And that kind of leads to Tony's comment is, annular flow makes sense, bigger flow area, less frictional pressure loss. But as your wells age, eventually you need to reduce that flow area to help stabilize that flow pattern.
That's correct. And it's a very valid thing to be aware of, and maybe concerned isn't the right word, but what is that longer term gas lift plan? What is the, I think I used the phrase earlier, kind of a cradle to grave. So, that's one piece that really makes me excited to have merged with you guys in Flowgistics too. But understanding some of those pieces, as I look back over the history of high pressure gas lift, I see that Estes has been really excited about it, and rightfully so. It's an amazing tool for operators and for the industry, but we tend to do the high pressure gas lift and then have kind of left that piece to the operators to figure out on their own later.
I see.
And as time has progressed and operators have, been at this point of, gosh, okay, what do we do now? Do we just keep high pressure out there forever? Well, the engineer in me says, well, that doesn't really make sense. So I think it's a very valid discussion, and I'm glad that we're partnered up together. I'm glad that we can bring that, and we will discuss that.
Yeah, I agree with you, and I think there's still a lot of things to learn and working with operators to understand, like, what is the process, what is the plan to mitigate things like slugging, like Tony mentioned, and basically too large of a flow area when your production comes down. What do you do with that high pressure booster compressor when it's not needed anymore?
Sure.
How do you plan to go from high pressure to, let's just call it low pressure now, and have a very seamless plan to do that? And so, that brings up one of the things too is, we've kind of touched on, what is high pressure gas lift? Your definition of it and how you view it. And that's a really good way to look at it. But then the other piece that I think about is, once you've kind of defined it, the next piece is, well, how do you set it up? And, fortunately for the compression side, it's all on surface, right?
It is.
So how do you set it up to initially high pressure gas lift? And then if you see things like instability, slugging,
Yep.
how do you, kind of remediate those things through the compression or through the surface setup?
Okay. So I hear your question here is what do we practically, what does that look like on the surface? If you'll allow, can we go back real quick to one other point you brought up, and then I'll fold it back in.
Okay.
One of the beauties of high pressure gas lift is that really we bring all of the problems to the surface, right? There's just almost literally nothing downhole to fail. We're putting a piece of pipe inside of a piece of pipe. We don't really use gas lift valves or not multiple. We talk multi-pointing in conventional gas lift is a challenge and has been a problem over time. You have increased, diameters of pipe as the mandrels, they could get stuck. And, that's been one of the beauties of high pressure gas lift is we don't put any of that downhole. There's no jewelry downhole. So I think as people are considering high pressure gas lift, what are some of the benefits? Why would I do this? That's one of the key points. In fact, that's really what caused the first operator that we worked with to consider high pressure gas lift. They were tired of the mandrels. They were tired of the problems they were having. Now, that's not to say that conventional gas lift is all bad. It definitely has its place.
Well, and to kind of add to that too, we're seeing a change in the thought process between high pressure gas lift in terms of planning for that low pressure side,
right,
and trying to, and I guess what I'm getting at with that is it is pushing a change in like equipment selection,
it is.
Manufacturing of the equipment, different equipment selections to where you can put that low pressure system in place during the high pressure phase,
Yes.
And still basically make sure that it works once you're ready to make that switch from high pressure to low pressure.
Right. So that's a good lead in for me to answer kind of your question. What does that surface installation look like? I mean, we've brought all of our really the equipment to the surface. So we're definitely talking about compressors, right? That's inevitable. We're talking gas lift. We're talking the pressurized and high pressure gas lift. So in conventional gas lift, we tend to have one compressor.
Mm-hmm.
And normally that would compress gas from about 50 psi is what many sites are operating at, what many separators are kind of set at, to about 1,200 pounds. That psi, that was the traditional gas lift pressure. Well, in high pressure gas lift, as the name suggests, we have to have higher or a relatively increased pressure. And so to do that, we have installed what some people have termed a booster compressor.
Okay.
And why?
And this is a secondary compressor from that traditional, I guess, like 3-stage compression that you typically see with 1,200 psi discharge.
That's exactly right.
Okay.
We're simply boosting that pressure up. So we're taking the 1,200 pounds psi of discharge from what we have called the feed compressor.
Okay.
Or the primary compressor. Different people use different names, but from that I'll call it a feed compressor. I like that because we're feeding our booster. So we take that 1,200 psi and then we're boosting it up to a higher pressure. Now, what is that? Well, it's different for every well. Could be as high as 4,000-ish. We see kickoff pressures anywhere between 2,500 and 3,500. I would say maybe north of 3,000 is very typical.
Okay.
So there's a lot of variation, but the point is that we are boosting the pressure up. So we really have two compressors in a setup. And I think we have a diagram here that might be helpful.
Yeah, we do. And while I'm looking for that, this is I'm going to classify it as a dumb question. Why not just have one compressor that goes from, say, 50 psi to 3,000 or 4,000 psi?
Well, it's absolutely not a dumb question. It's a very valid one. It's one that we've wrestled with ourselves early in trying to decide, all right, what is our solution? What is the strategy that we're going to offer? Um, our company elected to go the booster compressor route for a couple of reasons. Number one, we wanted to work with infrastructure that existed with operators. I mean, almost everyone that is doing gas lift, considering gas lift, even those who aren't, have some source of, typical gas lift pressure. So in the 1,000 to 1,200 psi.
Yeah, and that could be something as like a centralized injection gas lines where they just have a centralized compression facility and they simply just pipe out 900 to 1,200 psi to the well site.
Correct.
Or they could have, like you mentioned, the 50 psi sales gas pressure, and they go and set a compressor on that pad site that takes it from 50 psi to 1,200 psi.
Right. So we were just really wanting to work with what operators had in place, rather than to say, all right, well, let's get rid of all that and let's put something in brand new.
I see. Okay.
We wanted to recognize that existing infrastructure. Mm-hmm. The other piece that we recognize, we've already broached a little bit, and we realize there is a life of the well after high pressure gas lift. I think early on we always knew that there was going to high pressure gas lift tends to be a temporary or but a season in the life of a well, and that tends to be early in the life of the well from kickoff of the well until some period of time in, and you have a survey.
Yeah, I was about to say we have a couple surveys on that, but that makes sense, right? Is that we talked about the benefit of high pressure gas lift. It's just simple density reduction of the entire well bore, vertical well bore of those fluids, or near vertical well bore. So in my head, like what that tells me is if the well is producing 100 barrels per day, well, with traditional or low pressure gas lift, you're probably already going to achieve that single point. You mentioned it as poor boy gas lift.
Sure.
But if the well's making 5,000 or 10,000 barrels a day, so like the early on production, initial production of the well, then you can maximize that well's deliverability, the overall reservoir pressure after completion, to help either stabilize that high production rate or even possibly increase it over what its naturally flowing capabilities are.
Right. Yep. So kind of maybe coming back around full circle on why did we select the multiple compressors, the booster? We work with what operators have in place. So we have an existing feed compressor or primary compressor. You add the booster in to do high pressure gas lift, and then when that phase has passed, then we can simply subtract the booster compressor out, but you still have the feed compressor there.
Oh, I see.
Right?
So
it's
you
kind of
keep all the infrastructure in place.
That's right. You kind of have a modular approach.
I see.
Now, some of our competitors have taken the approach of, hey, we're going to have one compressor to go from 50 psi suction to 4,000 psi discharge. And is that wrong? No, I can't say that. I'm biased, right? And invariably, we like our solution better, but we feel like because we've thought it out and we've tried to come to operators, we've tried to come to the market with a solution that is very workable, that is most cost effective, that causes the least disruption. So that's kind of why we've taken that approach.
No, that makes sense. And I know we have the schematic here of how you guys recommend the setup.
Sure.
And you bring up a very valid point. And we see that from the poll data that we received, is that, typically most operators are viewing the use of the high pressure gas lift. And actually, it was interesting to see, it was about 50-50, 50% being 12 months or less, and roughly about 50% being 12 months or more.
Sure.
And so, and that, for me, that tells me that's based off of well deliverability, is that if you have a higher well deliverability, then that system's utilized longer. If you have, kind of that hockey stick production where it peaks up and then immediately drops down, then that's that sub 12 months. But what you mentioned by adding that booster in line with the feeder, which we show here in the schematic, is that allows you to essentially remove that booster and still keep your existing infrastructure
Sure.
For your low pressure or your traditional gas lift.
Right. And what we found is that a lot of operators that have said, gosh, we like high pressure gas lift. This is working well for us. And we want this to be a part of our artificial lift strategy, is that those operators will pick up kind of a miniature fleet, if you will, of high pressure gas lift compressors. And most of these are rental these days. And in this fleet, they will rotate them around. So we'll take a high pressure gas lift compressor and install it on the young number one.
Mm-hmm.
And then when he's done with using it on the young number one, he'll move it to the Nelle number one.
Okay.
And that it kind of becomes a mobile fleet of compressors that are rotated around. And so the operators that seem to do best with high pressure gas lift, and I look at it and I think, gosh, they're really doing a good job. It's taking a fleet, and it depends on how many wells and the size of the operator, but we see some with just a couple of high pressure gas lift boosters. We have others that are north of 100, a rather sizable fleet.
Mm-hmm.
But the point is that they are temporary and they are mobile. How temporary depends on the well. It depends on the basin.
I see. And that makes sense. And so you can set it up to where you can move those around based off of the need.
Correct.
If it's a new well, if it's an offset frac well that's been impacted,
Yes.
Things like that. And so in the schematic that you provided, so you have your infrastructure in place for traditional gas.
Correct.
And then you can set that booster essentially between you mentioned you called it a feeder compressor. Right. And your wellhead to take that feeder discharge pressure, which I assume is typically going to be like 1,000 to 1,200 psi.
Pretty typical.
Okay.
Fortunately, this booster compressor, the Wolf, as we call it with Estes, that's kind of our trade name for our high pressure gas lift booster compressor. It is a very flexible compressor on the suction pressure and the discharge pressure. But you're right, typical suction pressure to the Wolf booster compressor is 1,000 to 1,200 psi. Okay,
that makes sense. And then it essentially boosts it up to whatever your surface discharge pressure needs to be to either continue flow on a naturally flowing well, or to potentially, like worst case scenario, start up a well that has loaded up and died.
Right. And what is that typical pressure? We get that question all the time from operators.
We do too.
What is that pressure? And it's like, well, I can't tell you. I mean, that's kind of a physics or a guide question, right? What, how much restriction is there in the well, and what are the fluid levels, and that pressure even changes over time. Mm-hmm. What I can say is that when the booster compressor is first installed, you'll see a pressure, rise as you're displacing fluid between the tubing and the annular space. Mm-hmm. And once that gas gets around the end of the tubing, the single point of injection that we keep talking about, then we see kind of the pressure flatline, and then eventually the well starts unloading and we see it fall off.
That makes sense.
So the typical profile is rise real rapidly, flatline, and then slowly die off. Mm-hmm. To the point where we get to the discharge pressure of the Wolf high pressure gas lift booster compressor falls into the typical range of a conventional gas lift compressor, a 3-stage compressor as some people know it. And then we start considering, hey, is it time to subtract the booster compressor out and then move on to kind of the next phase or the next strategy of gas lift, which I think we want to talk about some here.
We do, and that's one thing that I get really excited for, is that, what are not only the surface, but what are the downhole things that you can implement typically early on to allow that flexibility, and not only of annular versus tubing flow, but also high pressure to low pressure. Yeah. And you're right, we'll touch on some of that stuff in terms of how do you determine when to switch? And then when you do make that conversion or that switch, what does that involve? Does that involve having to bring a rig back out and pull tubing again? Does that maybe involve a slick line run to defer a workover? Or in some cases, does that just simply mean a surface change, a control valve, or something like that at surface to make that change. And I think, this slide here kind of illustrates, at least from the surface standpoint, and we'll talk about the downhole, but like talking about the surface side, you mentioned having that flexibility. Can you walk us through, every operator is going to kind of do it differently, but a recommended, surface setup to integrate that high pressure system into the operator's current infrastructure?
Sure, and I appreciate the question. It's good, and I think everyone that is considering high pressure gas lift needs to realize that high pressure gas lift in most situations, perhaps not all of them, but in most situations is going to be a temporary artificial lift strategy. So you are prudent to consider what comes after high pressure gas lift and what can I do, probably in general, but especially on the surface to make that transition easier. And the operators that we work with that do that up front, we find that it's a pretty seamless, a very easy transition. So practically, what does that look like? Well, in this slide here, what we see is of course, a typical wellhead. On the right side of the screen, we see an injection line, and that is discharge of the high pressure gas lift booster. Mm-hmm. And we see that it is tied into the wellhead in two different places, both kind of on the bottom side, the casing valve, and then also we see up at the tubing valves. And the point here is to be able to switch very rapidly of the injection between the tubing and the casing. And then we see the same thing on the left side of the wellhead. We see a flow line, a production line. In other words, options between the casing, the annular space, or the tubing. Mm-hmm. And so let's talk maybe kind of number one, high pressure gas lift. So if we were going to do a high pressure gas lift installation, keep in mind we're injecting down the tubing. Mm-hmm. So we would close the casing valve on the right side, and then we would open the tubing valve such that high pressure gas is injected down the tubing. On the left side of the wellhead, we would we would produce up the annulus, and we would close the valve up on top to the tubing. So again, just to recap, we inject down the tubing and we produce up the casing. Now, at some point, it doesn't make sense to do high pressure gas lift anymore. Varies per well, but at the time which you say, gosh, I want to switch to more of a conventional flow. Mm-hmm.
Producing up the tubing and injecting down the tubing case and annulus.
Correct. We would flip-flop some valves. So we would inject down the annular space. So we would open up the casing valve on the right side. We would close the tubing valve, and then just the opposite on the production side.
So those, when we look at it as a quadrant, those four valves, we're basically just inversing each side based off of that flow path. And when I see that, that makes a lot of sense. And it also, for me, from an operations standpoint, it seems like, a service technician, a lease operator, AL tech, almost anybody that's approved to be on location can make that change. And like you said, make it relatively seamless. To integrate that in.
Yeah, there's no rig work. I mean, all of that expense, all of that downtime, all of the hassle is gone for a simple, foresight up front and saying, hey, for the roustabout crew, stay here an extra, I don't know, we're talking half day or day, makes life much easier down the road.
Yeah, that makes sense. And, when I look at the injection line, again, I tend to spend time on what we call low pressure gas lift. So 1,400 PSI or less. So typically, and again, operator, but a lot of times you can just take 2-inch threaded pipe and screw it together, right?
Right.
And meet that pressure rating that you need. But when you talk about having that booster at say 5,000 PSI potentially, in my head, those injection lines change, right? You're probably changing ANSI class. You're probably changing connections. Is that why we see everything flanged on the injection side?
That's right. It's simply a matter of pressure. I mean, in a typical well, 1,200 pounds, maybe 1,400 pounds max as you bring up. But those higher pressures do jump us up into a higher ANSI class.
Okay.
Now, some operators will use 1502 iron to connect between the Wolf booster compressor and the wellhead. We see that very commonly, and I don't have any reservations against that. So I don't think it's a matter of right and wrong, of good and poor practice. I think it really is up to the operator what the operator feels comfortable with. But it is definitely different than 2-inch screwed pipe.
Yeah.
I mean, we see a pretty high spec welded 2500 RTJ flange, or we see the 1502 iron. Those tend to be the two implementations of a high pressure line from the booster compressor to the wellhead.
Okay. And so that brings up something else, and I'll kind of jump back to the schematic. So when you talk about that setup, most likely for the operator, that's going to imply they're going to try to set that booster as close to the wellhead. Correct. While meeting all of their safety and operational goals as well, just to reduce that length of pipe between the booster and the wellhead.
That's right. I mean, let's be real honest. When we say high pressure, people just tend to get nervous. I mean, high pressure tends to be something that raises people's awareness. Is there a danger? And while we've seen just a history since really the earliest days of high pressure gas lift, a safety and an inherent lack of problems, people do have to be aware. And I think a practical implementation of that is setting the booster compressor definitely on the well pad.
Okay. That makes sense.
And making that high pressure line short. Maybe as much as anything, it's because the high pressure pipe is more expensive. Having welded pipe is more expensive, and people say, look, I just want to be very cost efficient on what we're doing. Or if you did the 1502 iron side, I mean, putting a mile of 1502 iron would be phenomenally expensive. So yes, practically the high pressure gas lift installations and specifically the compressor tends to be placed relatively close to the wellhead.
Okay.
Is there a prohibition or a reason that high pressure gas lift couldn't be centralized as we see in more conventional gas lift? No, I don't think so. I've certainly been part of some discussions with operators of contemplating that, but really I'm not seeing that too much.
No, and that makes sense. And I mean, I'll reference the offshore market is with gas lift in a offshore, primarily like a subsea application. Most of that is high pressure gas lift.
Right.
Now, of course, it's a lot more complicated. There is going to be downhole flow control devices, gas lift valves, and packers and things like that. But when you look at that is high pressure gas lift.
It is.
And a lot of times that compression isn't going to be on the platform. So they will pipe in high pressure gas from a compressor station somewhere for that offshore market.
Yeah, so it is kind of centralized high pressure gas lift. But we haven't seen that in the onshore portion of high pressure gas lift. Not because it can't happen, but that is not what operators tend to prefer.
Yeah, no, and that makes sense. And you have the infrastructure for the low pressure system, and to have that, like you mentioned with this schematic here, have that flexibility to switch back and forth. And in my head, when I think about unconventionals, is the big things from a production standpoint or from an operation standpoint is flexibility is key. Yes. We don't want to have to essentially touch these wells multiple times. So a lot of times the goal when we talk to operators is one solution to meet the ever-changing production and pressures that you deal with.
Right.
And so I see this from a surface standpoint too, is that less times we have to go and make changes, the better the well performs, and you get to kind of be relatively fluid with the dynamics of unconventionals, which is like an ever changing in production and pressure.
That's right. I agree with the flexibility piece because, none of this, we don't open a textbook and it says, well, you will do high pressure gas lift for 4 months and 17 days. It's different for every well. We know that rig schedules are tough. So flexibility is important, but we want to be smart with when we need to change. We want to be able to, as we would say, maybe spin on a dime.
Yeah.
Right? We want to be able to transition very quickly. And I think by implementing some of the strategies that we've talked about, starting with a wellhead of allowing injection either on the casing or the tubing, allow operators to be very agile in what they do and very cost effective too.
Yeah, that makes sense. And thank you for sharing that. And so I'll put you on the spot here. One of the things that I like to think about is, and this is a very big question, so take it for what it is, but like, how do you select a high pressure well or a well potential for a high pressure? And the way I think about it is like, is it depth driven? Is it liquid production rates? Is it formation gas rates? Like, what are some of the things that you guys run across in terms of what maybe makes a high pressure well and maybe a well that could just go straight to low pressure traditional gas lift?
Yeah, well, I mean, one of the beauties of high pressure gas lift, I would say maybe one of the crown jewels of high pressure gas lift is how flexible it is. So, I could say generically that really any well that we've run across is a high pressure gas lift candidate.
Okay.
Now, does it make sense in every one of those potential candidates? Perhaps not. The first thing that I think an operator would need to consider is, hey, where's my gas coming from? Now, we know that when we say we've got an oil well, in reality, it is also a saltwater well, it is an oil well, and it is a gas well.
Right.
Any well that's producing has all three components.
Unfortunately, yeah.
Right.
They haven't figured out how to just find oil and gas wells.
But they tend to be characterized or dominated by one or the other. And so they're inherent to the gas lift process and baked into the name is gas lift. So we have to have a source of gas.
Okay.
I think that goes without saying, but we have to be real clear. I mean, there has to be an adequate source of gas.
And that's a really good, clarifying piece is that's the same thing with traditional gas lift.
Right.
There's a lot of wells, especially in like the exploration side of the business or some of the different basins that just simply haven't caught up with the gas handling piece.
Right.
And so you look at a well and say, this is a great gas lift well, but you either have access to no supply gas or it's like sour gas.
Sure.
And it's like, well, unfortunately, you need to look at ESP or jet pump typically because you don't have that supply gas.
That's right. So, number one is obviously gas. And maybe to put some numbers on that, I mean, we see a GLR, kind of a desirable would be north of 1,000 cubic feet per barrel.
Per barrel, correct, yeah.
Now, certainly we can supplement that. I mean, we could do a purely oil or water well. We could lift it with gas lift, but we have to bring all of that gas in. And then you're dealing with infrastructure. Do I have buyback capability? And it just makes it a less compelling argument towards high pressure gas lift if you're having to bring all of the gas.
Okay.
So it's good for the formation to be giving up some gas.
I see.
So that would be one thing. I would say another thing is high pressure gas lift is really focused on high fluid lift rates, high lift rates. And so if your well is giving up but a couple hundred barrels of oil per day, I wouldn't come in and say, hey, well, let's just go to high pressure gas lift. It makes tons of sense. I mean, we do have an additional compressor that is needed. I mean, so that is an additional expense that has to be offset by something. So really the best candidates tend to be early in the life of the well where you see the large production lift rates.
Yeah.
Some people have asked us over time, well, who are your competitors? And they don't tend to be the other compressor companies as much as they are other artificial lift methods. So such as an ESP, right? ESPs are very popular early in the life of the well because the fluid lift rates are just so high. I mean, we see people lifting 5,000 to 10,000 barrels a day with ESPs. And that's also where high pressure gas lift value proposition is in the high fluid lift rates. So, taking just a quick rabbit trail, and talking kind of competition in some of the other artificial lift methods. I mean, ESPs do a great job of lifting fluids.
Yeah, they do.
However, when you start getting a gassy well, then you start to see some problems arise, and certainly there's a lot of technology being developed for ESPs to try to deal with that gas, and it's successful to varying degrees. But ESPs don't tend to have a history of being real successful with gas. But high pressure gas lift, I mean, we have to have gas. It's required. So a gassy well where we're trying to lift high volumes of fluid. And then I think the other piece that I would offer up are that solids laden production. Well, what unconventional well these days does not have some solids in it, namely sand, right? Yeah. I mean, that's how we've been able to achieve these wells that produce such high volumes of fluid and of oil is by fracking them. We pump sand, we force it into the reservoir. And so
you have to handle some of that sand flow back.
That's right.
Yeah.
That's right. So we just don't have any downhole jewelry. The gas lift valves to be cut out early in the life of the production where that sand is still trying to settle or some of it's coming back up. We don't have any valves really to cut out. So that's really where high pressure gas lift is shined in gassy wells, in high production, and in solid laden production.
Okay, and that makes sense. And that actually leads to a question that Drew had is when you're implementing this high pressure gas lift, GLR is always a function, right?
Sure.
Of any kind of artificial lift, you have to account for your GLR, which is your gas to liquid ratio,
right,
like you mentioned, as standard cubic feet per barrel. But one of the things that Drew had a question on is as that GLR naturally increases in the well, does that hinder production? Does that help production? How do you see that from a high pressure standpoint?
Well, it actually really helps it because the more gas we have coming up, the more it tends to help unload the well.
Okay, and that makes sense from like a traditional gas lift standpoint.
Sure.
Too, is that it really almost any well, as long as it has source gas, can be a gas lift well. But you tend to want to find higher formation GLR, gas to liquid ratio wells, because that extra gas from the formation just further improves the efficiency of the system. So that's a really good question. And that's a really good point on that. And so I want to kind of take that to one of the big questions that we get asked frequently, and I imagine you do as well, is kind of go back to this bullet point here, is how do you identify your surface injection pressure?
Sure.
So it sounds like that booster that is set has a pretty wide flexibility in terms of discharge pressure. But one of the big questions is like, well, if I have a 8 or a 9,000 foot well, and let's say worst case scenario, it's completely loaded up. Like by the time the rig gets out there to install tubing, by the time the surface plumbing, flow lines and everything has been set, well's no longer flowing. And so it's a very easy problem calculation to solve, but it's a very common one that we see.
Yeah, and I agree. It is very simple, but it is very common. And so let's just kind of look at it from a physics perspective, and we won't nerd out too much on the math, right? But we can go back to the physics equation, which says P, the pressure, is equal to rho GH, or the density times the gravity times the height of our column of fluid.
And that's where I have here is your fluid gradient defined as like your PSI per foot.
That's right.
Multiplied by your TVD of your well.
Yeah, and so a fluid gradient, of straight water is about 0.43 PSI per foot.
Yeah.
Maybe a salt water would be, what would you say, a half?
0.465, maybe 0.5.
Okay.
Yeah.
But somewhere in the 0.4 range, and then we just multiply it times the depth of our well, TVD. Right, and so we see those nominally 10,000 feet, or in this case, you've called it out.
8,800, yeah.
Right, and so we simply take that fluid gradient pressure and the depth of the well, and we come up with this nominally 4,000 psi.
Yeah,
So-
that makes sense. And that's worst case scenario,
That's
right?
right.
Like just like traditional gas lift, ideally we want to catch the well in a flowing state for a multitude of reasons. One, we have less downtime. It's easier to start the system up.
Right.
You don't have any of those lost production days. But in a case where it's like, okay, let's view this as worst case scenario, well's just not producing.
Right.
Yeah, like you mentioned, you need roughly 4,000 or 4,100 psi at your end of tubing to displace that fluid.
Right. Kind of a kickoff state.
Mhm.
Right.
Yeah.
And we definitely have seen that before. Perhaps the highest kickoff pressure that I've seen, I want to say, is in the nominally 4,500 range, but I mean that's not typical, but we've done it, and it works well, and it tends to be very short lived. Just as soon as that first slug or bubble of gas gets around the end of the tubing and into the annular space, you start lightening that column, and it falls off pretty quick.
Yes, sir, and I can see that. And like once you get into that flowing state, your surface injection pressure is going to simply decrease to match what your flowing pressure is.
That's right.
And then, of course, backing out what that surface injection pressure is. So if we have roughly 4,100 PSI at the end of tubing, then once we kind of back out that density weight of the gas, then, you're left with approximately 3,350 PSI of surface injection pressure to essentially start that well up.
Correct.
And then once you achieve that density reduction, then that injection pressure is just going to trend with your flowing bottom hole pressure.
That's correct.
So no, that's good. And Will, we could talk about this all day long. But one of the things that I wanted to touch on real quick, because of course we're running out of time, and still be able to catch some of the questions, is, we talked about why you would go with high pressure gas lift. And the next two slides kind of illustrate that. And so what we're looking at is a deliverability of the well, highlighted in green, versus the just simply hydraulics or the pressure changes between traditional gas lift, not lifting at the end of tubing, and high pressure gas lift lifting at the end of tubing.
Right.
And early on, you look at a traditional well like this, well, the difference between traditional gas lift and high pressure gas lift are almost 1,000 barrels per day.
Correct.
So that makes sense why we would want to go to potentially a high pressure lift around into tubing.
Right.
But we know that well's overall deliverability is going to change. It's going to reduce.
It does.
The pressures are going to come down, and eventually those two models are going to either touch or get relatively close to each other. And so for me, when I think about conversion, high pressure, low pressure, I like to look at it as kind of two different ways. I love rules of thumb. Like the oil field lives and dies off rules of thumb. So one of my rule of thumb for conversion from high pressure, low pressure is just simply when that booster discharge pressure hits your feeder discharge pressure of the compressor. So example is if your feeder compressor discharges at 1,200 PSI and your booster discharge pressure has reduced down to 1,200 PSI, pretty simple, indicator to make that switch.
Well, it is. I mean, it's just the booster compressor is not doing any work, right?
Yeah.
So from a logical perspective, you would say, why am I paying for this to do nothing? I mean, that's a great way to look at it.
And so that's one way I like to look at it. Of course, if we want to go into the hydraulic modeling, the engineering side, I like to really utilize hydraulic models for that. And eventually, when your production rates decrease to handling capacity of your tubing and your traditional system allows you to lift deeper into the well, you typically get something like this, to where the change in production between single point high pressure and traditional low pressure is marginal enough to where, that can be just a error or, that can be a rate that makes sense to make that change.
Correct.
And for me, the operator, and I know we're running out of time, working with operators to figure out, does that also include a workover rig to implement the traditional gas lift equipment? Is that a slick line change? or is that just simply like what you showed in the picture of the wellhead, just a valve change to achieve that? So, guys, I apologize. We could talk all day about this, and we do appreciate Will coming on board, but want to wrap it up and conserve everybody's time. But we will post this online, so it will be viewable on YouTube for anybody that had to get off or wasn't able to make it. We'll continue to have these e-learning series month over month, and most importantly, we want to thank you for coming out here and taking the time to just sit down and discuss this with us and really hopefully educate the audience.
Well, Matt, and to our viewers, I'm just really appreciative and honored to be part of this. It's fun to talk about high pressure gas lift. I've done it for the past, 7 or 8 years of my life, and it's really been a fun thing. But watching the operators say, gosh, this is a great tool for us. And so we just want to continue to educate. And I hope that folks will reach out via LinkedIn or whatever it is and continue the conversations.
Yeah, definitely. Yeah, thank you. And guys, thanks for joining. And if you have any other questions, let us know. If you missed any section of it, we'll post it on YouTube, and you guys can go back and watch it then.
Great. Thanks, Matt.
Yep. Thank you, Will.
We'll see you.
Thanks, guys. See
Bye.
ya.